Tornadoes are one of nature's most terrifying phenomena. On hot summer days, they appear out of nowhere, spinning themselves up to breakneck speeds before petering out into nothing.
I live in the area
leaving only a
that has
trail
tornado
of destruction
warning, so
in their wake.
it's gonna be a good one.
But not all tornadoes are created equal. On one humid May afternoon in 2013, the sunny skies over central Oklahoma darkened. Deep purple clouds, the colour of a bruised plum, blocked out the sky as a huge supercell storm brewed. And before long, it birthed the mother of all tornadoes. This is the story of a storm so vast, it became almost impossible to recognise what it was. A twister that in less than 60 seconds expanded from a slender rope to a monster more than 4 kilometres wide. Its chaotic winds reached record-breaking speeds and claimed the lives of those trying to measure it. To this day, it remains the biggest tornado the world has ever seen. I'm James Stewart and you're watching Astrum Earth. Join me today as we dissect the anatomy of the largest tornado ever recorded, uncover the physics behind its erratic behaviour, and pay tribute to the scientists who gave their lives trying to understand it.
What an intro by him. By the way, this is Astrum Earth. And I am Big Man Mac, or as if you go on Twitch, the official Mac. And yeah, this will be stuff. I like that intro so much. Get right into play Until Dawn.
In many ways, Oklahoma weather in late May could be described as quite agreeable. Warm, sunny days, not too hot or too cold at night. But don't let this deceive you. These warm and pleasant days can all too often be cooking something sinister. Oklahoma sits at the heart of Tornado Alley, a geographic corridor in the central US where the continent's most volatile air masses collide. And the 31st of May 2013 was not just a normal spring day. Less than 2 weeks earlier, the state had seen an EF5 tornado, the strongest possible on the EF or enhanced Fujita scale used to measure these storms, ravage the city of Moore. Even now, that was the costliest tornado ever to hit Oklahoma. Now, the air was hanging heavy near the city of El Reno, just 50 kilometers from Moore. The atmosphere was primed with a volatility that any meteorologist would recognize in a heartbeat as being absolutely perfect for forming a tornado, also known as a twister. Conditions that would entice any storm chaser worth their salt straight there. Let's get right down into it and break this atmospheric powder keg down into its ingredients. Firstly, the air was extremely unstable. And what do I mean by that? Well, the sun had been baking the warm Oklahoma plains, heating the ground and the air above it. As warm air is less dense than cold air, it will rise like a hot air balloon for as long as its temperature remains warmer than the air around it. The amount of energy available to form these rising pockets of air, causing updrafts, is called the convective available potential energy, or CAPE for short. On a normal, severe weather day, CAPE values might reach between 2,000 or 3,000 joules per kilogram. On May the 31st, CAPE values over central Oklahoma were around 4,500 to 6,000. In other words, there was a lot of energy in the air, and that powder keg was just waiting for a spark. In addition to this large CAPE value, there was plenty of lift. A cold front was moving down from the northwest, and a dry line, the boundary separating moist Gulf air from dry desert air, was coming in from the west. The intersection of these boundaries is known as the triple point, and it acts a bit like a wedge, violently forcing the unstable high Cape value air upwards. These two ingredients will together make a thunderstorm, but you need something more to make that storm spin up into a twister. Wind shear, or the change in wind speed and direction with height. In Oklahoma that day, warm, moist winds were blowing from the southeast, but a couple of kilometers up, they shifted to the south, and higher still, the jet stream was screaming in from the west. This turning of the winds with height creates tubes of horizontal rotation in the atmosphere that spin invisibly in the clouds. When those explosive updrafts caused by the high Cape punch through these rolling tubes, they tilt them vertically. The tubes stand on end. And suddenly you don't just have a storm, you have a supercell. When I'm researching supercells, I like to do so with a super browser. So I recently switched to Opera, a faster, smarter web browser with some incredible features on it, clicking the link in the description. A supercell is the king of thunderstorms, a tall storm cloud with an anvil-like shape that stretches out across the sky. These are the rarest type of thunderstorm, with a deep, persistently rotating updraft called a mesocyclone. Think of the mesocyclone as the engine of the storm, a dangerous carousel of air, miles wide, rotating counterclockwise. And in the right environment, not only can these storms last for hours, but if the rotating winds start to drop down from the clouds, they can form strong, intense tornadoes. Really big twisters are the stuff of nightmares. They are huge, spinning vortices of air that can clock wind speeds of 450 kilometers per hour, tearing trees from their roots, peeling asphalt from the streets, and even lifting entire houses clean off their foundations.
That's crazy.
According to the US National Weather Service, on average 800 tornadoes are reported every year in the US alone, resulting in around 80 deaths annually.
800 tornadoes and 80 deaths. That is insanity. I'm right in the middle of this stuff. Bah.
So far, so terrifying. But what happened in El Reno on the 31st of May 2013 would challenge our fundamental understanding of how tornadoes are formed. The classic model taught in meteorology classes was that tornadoes formed via rotation starting high up in the storm and gradually stretching down to the ground, prompted by something called a rear flank downdraft, dragging the rolling tubes I mentioned before down to the surface. Forecasters and storm chasers would watch their radar screens, seeing the rotation tighten up in the air and waiting for it to descend into what's called the dynamic pipe effect. But this wasn't what they saw that afternoon in El Reno. A supercell formed, but it was no ordinary supercell. This was a high precipitation, or HP, supercell. In these storms, the updraft is so strong and moisture so abundant that the rain wraps all the way around the mesocyclone. Tornadoes forming in an HP supercell can be shrouded in a curtain of rain and hail. Adding to the drama was a cap, a layer of warm air that sits aloft and acts like a lid on a pot of boiling water. Air parcels that rise into this layer become cooler than the surrounding air, which stops them rising further and producing thunderstorms. And this suppression can be dangerous. It allows heat and moisture to build up underneath the cap, with pressure mounting until the lift becomes too strong and the cap breaks. And that's exactly what happened at around 4:30 PM that day. What followed was an explosive development of the storm, with towers appearing from nowhere and rocketing to 15,000 meters into the stratosphere within just 16 minutes. By 5:35 PM, just an hour later, the first tornado from this enormous cloud had touched down in Kingfisher County. But the main event was brewing further south. At 6:03 p.m. CDT,
That tornado went.
but the main
Let me
event
get back
was
to it.
brewing further south. At 6:03
The tornado went from here at 6:04. Yeah, 6 all the way. It
p.m.
moved that
CDT,
fast.
a few
That
miles
time span.
southwest of El Reno, the rotation reached the surface.
Tornado!
Initially, it didn't look like much. Photos from the first few minutes saw a small, dusty whirl under a dark, brooding wall cloud. For those living in Tornado Alley, it would have seemed like just a small one. I can navigate around that, no problem. But the radar data recorded that day tells a different story. What the researchers found, in my book, makes tornadoes more menacing than ever. Storm researchers Dr. Jana Hauser and Dr. Howard Bluestein were parked on a nearby overpass with their RAXPOL, Rapid Scan X-band Polarimetric Mobile Research Radar. This emits pulses of microwave energy that bounce off precipitation and debris, allowing scientists to analyse the intensity, rotation and structure of a storm. The RAXPOL scan the storm every 2 seconds, far more regularly than the standard National Weather Service NEXRAD radars, which take 4 to 5 minutes to complete a scan. Hauser and Bluestein's high-speed data revealed that in the minutes before the tornado became visible, the rotation at 20 meters above the ground was already tornadic, while the rotation at 1 kilometer up was still broad and disorganized. In other words, this tornado did not descend from the clouds, no. That strong rotation existed at the surface before it existed above. It was building up from the ground. So why does this matter? Well, it matters if
that's
you're
cool,
waiting
look.
to see a funnel cloud drop from the sky to issue a tornado warning. Because if the danger is already on the ground, invisibly churning up the dust and just waiting to connect with the cloud and unleash its full power, that warning will come far too late. In fact, this bottom-up genesis could explain why the El Reno storm caught so many off guard. This twister didn't just grow upwards. Within minutes, the tornado started to metastasize, rapidly ballooning in width. By 6:19 p.m., just 16 minutes after formation, the tornado crossed US Highway 81. Now, when you normally think of a tornado, you might imagine the Wizard of Oz classic, a sort of slender funnel snaking down from the clouds. But this behemoth storm had become a wedge. It no longer really looked like a tornado at all. In twister terminology, a wedge is a tornado that is wider than it is tall. But even that description fails here. The base of the cloud dropped significantly until it was almost on the ground. The entire rotating wall cloud became the tornado. To an observer on the ground, specifically one to the east, the direction the storm was moving in, it wouldn't look like a funnel at all. Instead, it would appear to be a dark, horizon-spanning wall of fog and rain, indistinguishable from the background sky. And this monstrosity hiding in plain sight was still growing. Radar measurements confirm
That
that
whole
at its
wall was the
peak,
tornado?
the width of the tornadic winds reached an extraordinary 4.2 kilometers. Let that sink in. That's roughly as far as the eye can see to the
I'm chatting
horizon.
with Muggy.
2.6 miles. Nearly 14,000 feet, a tenth of a marathon. The width of Manhattan Island at 42nd Street. Just imagine a wind vortex spanning across New York City from the Hudson to the East River, grinding everything in between. This tornado broke the previous world record for width, held by the Hallam, Nebraska tornado of 2004, by nearly 200 meters. But size was only
Damn.
half the equation. The other half was speed. Inside this 4.2 kilometer wide circulation, something even more incomprehensible was happening. The El Reno tornado had become a multiple vortex tornado. It was no longer just one spinning column of air. It was a spinning wheel of multiple smaller, more intense tornadoes all rotating around a common center, creating the maximum possible devastation. And these sub-vortices can be incredibly powerful. Think of a figure skater spinning. When they pull their arms in, they spin faster. Well, the same thing's happening here. The core circulation becomes unstable and breaks down into smaller eddies. Each of these eddies, the sub-vortices, pulls in just like that figure skater, condensing the angular momentum into tight pillars of wind, moving fast. Two particular mobile Doppler radars.
That's that is absolutely insane. Because that was a bunch of small tornadoes spinning rapidly in a circle. That's
For
why
measuring the storm that day, RAXPOL, which I've already mentioned, and another called the Doppler on Wheels. They capture wind speeds that are, quite frankly, hard to get your head around. One subvortex was clocked with a ground relative wind speed of 504 kilometers per hour. For context, the strongest wind speed ever scientifically measured on Earth was 511 kilometers per hour in the Bridge Creek Moor tornado of 1999. El Reno was just shy of the all-time world records, and arguably, given the limitations of radar sampling, we only see a snapshot every few seconds, it may well have exceeded that speed in between scans. I mean, this is already terrifying enough, right? The biggest tornado the world has ever seen has just grown a bunch of extra vortices that also make it possibly one of the fastest tornadoes ever, but we're not stopping yet. Oh no. These subvortices weren't just orbiting the center, they were moving around the ground at varying speeds. At times, the main tornado was moving east at 50 to 65 kilometers per hour, 30 to 40 miles per hour. But the subvortices rotating within it would swing around the southern edge and shoot forward at speeds of 270 to 290 kilometers an hour relative to the ground. When they looped around the northern side, they would fight the forward motion of the parent storm and essentially stand still, or even loop back west in what we call trochoidal motion. Can you even imagine the absolute chaos of storms within a storm, of differing forces, speeds and directions all clashing together in a frenzy of devastation? It's madness. The best thing I can come up with to give you at least an idea of what was going on here is probably a spirograph toy. I always wanted one of these when I was a kid, actually. So with a spirograph, the pen moves around in circles while moving forward, creating those curly looping lines, yeah? Well, that's the kind of path these subvortices took across the Oklahoma farmland. This trochoidal motion made the El Reno tornado incredibly deceptive. If you were a storm chaser driving parallel to the tornado, as storm chasers often do, you might think you were safe. You'd match the speed of the main funnel at a safe distance. But not with this monstrosity. A subvortex is incredibly unpredictable and could suddenly swing out from the rain curtain, accelerating from 0 to 160 kilometers per hour forwards in seconds, closing the gap before you could even shift gears. I don't know about you, but I'm exhausted by this already just watching, and I'm afraid this storm had more horrors to offer. The supercell also produced a satellite tornado. This wasn't a subvortex inside the main circulation. This was a completely separate tornado that formed to the southeast of the main wedge, and it was anticyclonic. In the northern hemisphere, 99% of tornadoes spin cyclonically, or counterclockwise, as they are indirectly influenced by the Coriolis effect. They usually spin in the same direction as the supercell they are associated with. Anticyclonic tornadoes can exist though, and they spin clockwise. Now these are rare, usually weak and short-lived tornadoes. The satellite tornado that grew alongside the main twister was a monster in its own right, a huge multi-vortex anticyclonic beast. It formed along the rear flank gust front, rotating clockwise and dancing alongside the main cyclonic wedge for nearly 15 minutes. So now you had a 4.2 kilometer wide cyclonic wedge to the west and a powerful anticyclonic satellite to the east, grinding across the landscape in a grim, almost totally unpredictable dance. It must
This is
have been
crazy.
utterly petrifying for anyone witnessing it. It's petrifying watching it back now. Now, while I'm guessing most of us will be doing everything in our power to get as far away from all of that as we possibly could, one man was doing the complete opposite. On the trail of this monster storm was one of the most well-known storm chasers in the world, Tim Samaras. Tim was not a thrill seeker or adrenaline junkie. He was an engineer, a scientist, and a meticulous researcher. In the world of storm chasing, few names commanded as much respect. Tim was famous for designing the Turtle, a hardened probe that looked like a sort of squat flying saucer. His goal when chasing storms was to place these probes directly in the path of a tornado to measure wind speeds and drops in air pressure at the surface, data that radar beams cannot see as they overshoot the horizon. He had successfully deployed these probes in front of violent tornadoes before, including the Manchester, South Dakota F4 storm in 2003, where he documented a record-breaking pressure drop of 100 millibars. Tim was known as the safest chaser in the business. He didn't take unnecessary risks. He studied the data, learned everything he could about tornado meteorology, and always planned his intercepts with mathematical precision. On May 31st, 2013, Tim was leading his research team, TwistX, Tactical Weather Instrumented Sampling in Near Tornadoes Experiment. With him in his white Chevrolet Cobalt were his son, Paul Samaras, 24, and a videographer, and Carl Young, 45, a meteorologist and longtime storm chase partner. They were actually out on a different mission, chasing unusual lightning, transient luminous events or TLEs in superstorms on the plains. Tim and his team had missed out on the Moore tornado 10 days earlier and had seen the conditions brewing around El Reno that day. They were scheduled to be further north on this occasion, but decided the potential for a huge tornado would be too good to miss. So they decided to head south to attempt to deploy pods in the path of the El Reno storm. The aim was to gather data on near-surface winds, data that could help engineers build stronger houses and potentially help save lives in the future.
Oh, that's cool.
At approximately 6:20
That's
p.m.,
actually very cool.
the TwistX team was driving
They're
east on
stronger
the
houses
Reuter
and help
Road,
save people.
a gravel road south of El Reno, running parallel to the tornado. Ahead of them was another chaser, Dan Robinson in a Toyota Yaris. Dan's rear-facing dashcam captured images of the TwistX vehicle. They were headlights in the rain, following the grid road, keeping pace with the storm. But the storm was changing. Remember the expansion before? At 6:03 p.m. the tornado was small, but by 6:24 p.m. it was 2.6 miles wide. The TwistX team and Dan Robinson ahead of them were not driving next to the tornado anymore. Because the tornado was wrapped in rain and because its outer circulation had expanded so rapidly, the edge of the storm was much closer than it appeared visually. The wall of rain wasn't just rain, it was the outer wall of the 500km/h vortex, and they were driving straight into it. We can only tell the rest of this story because the timeline of their final chase has been reconstructed through GPS logs, radar analysis, and dashcam footage from other chasers, like Skip Talbot from Skip Talbot Storm Chasing, who very kindly helped us with footage and maps in this video. Thank you so much, Skip. You can see more tornado footage from him at the link here. When hunting a tornado down, storm chasers look for what's called the inflow notch, a clean slot of air feeding into the tornado. This usually signifies the leading edge of the storm. However, as the El Reno tornado expanded, the inflow notch began to close up or wrap around. The clear air they were driving in was actually being pinched off by the expanding circulation. Tim Samaras, astute observer that he was, likely realised this. He remarked on the radio, "There's no rain here, we're in a bad spot." Being in a rain-free area when the storm should be raging implied they were deep in the inflow jet, directly in the path of the expanding vortex, rather than safely on the periphery. Then, the tornado did the unthinkable. It turned. Instead of continuing east-southeast along the path any seasoned storm chaser would expect it to take, it hooked sharply north, then curled back. But while the centre of the storm turned, the southern flank of the tornado, the wind field, surged outward. Dan Robinson, still ahead of Tim, realised something was wrong. He floored the car and pushed through the storm. Tim, Paul and Carl, however, were just 20 or 30 seconds behind him. And those 20 seconds in this case would prove to be the difference between life and death. As the Twistex Cobalt moved down Reuter Road near the intersection with Radio Road, a violent sub-vortex swung around the southern edge of the parent tornado. It didn't just hit them, it swallowed them whole. Radar analysis suggests the winds in this specific sub-vortex were approaching 320 kilometers per hour. The Chevy Cobalt, weighing 1.3 tons, was lifted and thrown nearly 800 meters through the air. When the wreckage was found, it was unrecognizable. The 3 men were killed instantly.
Rest in peace, those 3 men. Like that just shows you how dangerous generally. You know, they're scary. Very scary. Probably the scariest natural disaster you can cross. Like, I'd rather deal with a volcanic eruption than be. That's me being honest.
This was the first time in history that storm chasers had been killed by a tornado. It sent a shockwave through the community that is still felt today. If Tim Samras, the cautious, calculating expert, could be caught, then no one was safe. And it wasn't just Twistex. One of the tornado's sub-vortices had just narrowly missed Mike Betts and the Weather Channel Tornado Hunt crew. Their SUV was lifted and rolled nearly 200 meters into a field. They survived with just injuries, but their vehicle was crushed flat. Another amateur chaser, Richard Henderson, stopped to take a photo. He sent it to a friend with the caption, "Funnel." Moments later, the tornado overtook his position. He too was killed.
Oh wow.
In total, 8 people died in the El Reno tornado, all of them inside vehicles.
Rest in saw them. A baby died to this? Oh no. That was the mother. Yo, rest in peace to all these people that died. Like, seriously. That is crazy.
How do you even begin to make sense of a tornado of that scale? How do you rate a tornado like El Reno? Well, traditionally the Enhanced Fujita or EF scale is the industry standard for rating tornadoes. It ranges from EF0, which is weak, to EF5, which is incredibly violent, often leading to total destruction. But here's the catch. As you can see, the EF scale is a damage scale, not a wind speed scale. An EF5 rating requires finding specific damage indicators. Well-built houses swept clean off their foundations, skyscrapers deformed, asphalt peeled from the road. The El Reno tornado luckily passed mostly over open fields. It hit cow sheds, fences and a few structures, but it largely missed the populated subdivisions. The structures it did hit were rated EF3 damage, but the mobile radars had measured winds of 476 to 503 kilometers per hour. Winds that fast are, by definition, well into the EF5 range, which starts at around 320 kilometers per hour. Leave a tornado emoji below if you think El Reno should have been an EF5.
Yeah.
So the National Weather Service in Norman, Oklahoma faced a dilemma.
It should definitely
Do they
be
rate
an
it based on what
EF5.
it did, EF3 damage, or what it was, EF5 winds? Initially, they upgraded it to EF5 based on the radar data.
Good.
It was a landmark decision, acknowledging that technology allows us to see the wind even if it doesn't hit a house. But months later, in August 2013, they reversed the decision. The El Reno
Why?
tornado was downgraded to EF3. The official reason? NWS policy for determining EF ratings is based on surveys of ground damage. Because the fastest subvortices hit wheat fields and not buildings, the record books will forever list the widest and possibly strongest tornado in history as merely an EF3. This decision sparked fury in the meteorological community. Critics like Dr. Josh Werman argue that ignoring the radar data is dangerous. It essentially says if a tree falls in the forest and no one is around to hear it, or if a tornado spins at 300 miles per hour and doesn't hit a house, it didn't make a sound. It affects engineering standards too. If we assume tornadoes only reach EF3 strength in this region because that's what the damage says, we might underbuild critical infrastructure like nuclear plants, hospitals, or even schools. The El Reno tornado highlighted a glaring flaw in our classification system: the disconnect between the hazard, the wind, and the impact, the damage. To the scientists who measured it and to the families of those lost, there is no doubt it was an EF5. The El Reno tornado of 2013 stands as a grim milestone in severe weather history. It forced a re-evaluation of safety protocols. For one, the safe southeast quadrant of the tornado is no longer assumed safe when dealing with massive erratic wedges. It also prompted a debate about chaser convergence, that is to say, the sheer number of people clogging the roads, potentially blocking escape routes, which is only growing as amateur storm chasers vie to get new footage. On that day, thousands of locals, spooked by the Moore tornado just 11 days prior, had fled their homes, jamming up the interstates. If the El Reno tornado had not lifted before reaching the traffic jam on I-40, the death toll could have been in the hundreds. But scientifically, El Reno gave us a lot of data to think about. We now know tornadoes can form from the ground up. We know they can expand to unimaginable widths in seconds. We know that subvortices can move at racing car speeds inside the parent circulation. As little comfort as this may be, Tim Samras and his team did not die in vain. The data they collected and the data collected by the radar teams around them has advanced our understanding of tornado genesis more in one day than in decades of theory. They stared into the abyss so that others wouldn't have to. The 2013 El Reno tornado remains an outlier, a freak of nature that pushed the boundaries of size and speed. It's a humbling reminder that no matter how much we study the atmosphere, no matter how many radars we build or how many papers we write, there is still a wildness to the wind that cannot be fully tamed. It reminds us that the line between observer and participant is thinner than we ever thought. We watch the sky with a little more caution now, a little more respect. And I know I, for one, won't look at movies like Twister in the same way again.
Dude, what a great video. Like an absolute subscribing to this guy. That is so well put. Yeah, facts.